There, Mr. Sutton here, bringing you the Algebra 2 Honors 11.5 Part 2 homework solutions on recursive sequences. For this problem, they want a recursive rule for this sequence. So since we have a linear sort of pattern going on here, this is one of those arithmetic sequences written in explicit form. Since it's arithmetic, my recursive version of that is going to be a sub n minus 1 plus the common difference d. So I just need to write the a1 and rewrite this rule with something filled in for d, and I've got my sequence. So for my a1, I just need to plug 1 into the explicit definition here. So 3 plus 4 times 1. 3 plus 4 is 7, so there's my a1, there's my base case. And now I just need the common difference. Since my slope of this thing is 4, that's what I'm adding each time to get each subsequent term of this sequence. So I'm just going to use 4 for d, so a sub n minus 1 plus 4. For this problem, they want us to turn this explicit sequence into a recursive rule. So let's start by identifying what type of sequence this is. Since we have an exponential piece here, this is a geometric explicit definition. So that means I can use my recursive geometric definition, r times a sub n minus 1. For the a1 I also need for the recursive definition, I just plug 1 into this expression they gave me. So 12 times 11 to the 1 minus 1. That's 12 times 11 to the 0, so 12 times 1, which is 12. And now for the recursive rule here, I just need the r value. Since I'm raising 11 to the power, that's what I'm multiplying by over and over again. So I'm just going to do 11 times a sub n minus 1. To write a recursive rule for this sequence, it helps to recognize from the linear nature of this that this is a arithmetic sequence. So that means we're going to be using a sub n minus 1 plus d for my recursive sort of equation here. Let me get the a1 first though. So if I do 9 minus 5 times 1, just plug 1 into this thing, that's going to be 4. And now my common difference, since I've got this negative 5 slope on my linear function here, that's what my common difference is going to be. That's what I'm subtracting each time. So I will write a sub n minus 1 minus 5 then for that recursive definition. For this problem, and the next two after this actually, we've got a recursive definition and we want to make it an explicit rule. So for this one, since we have a sub n minus 1 plus or minus a number, that is an arithmetic sequence. That's what we recognize from that. So my arithmetic explicit definition, we have a sub 1 plus d times n minus 1. A sub 1 in this case is 3, so we can plug that right in there. And then for my d, that's the thing that I'm subtracting each time here. So that'll be a minus 6 times n minus 1. And then I have to simplify this. So 3 minus 6n plus 6, and that's going to be negative 6n plus 9 if I fully simplify that. To turn this recursive definition into an explicit rule, it helps to recognize from this multiplication in the recursive part that this is geometric. So the explicit geometric form, that's a sub 1 times r to the n minus 1. a1 in this case is the negative 2 that they handed to us. For the r value, that's what I keep multiplying by in the recursive part here. So r is just going to be 3. So we have negative 2 times 3 to the n minus 1. To write an explicit rule for this recursive definition, it helps to recognize from this multiplication that this is geometric. So we're going to be using a sub 1 times r to the n minus 1 for our new form of this. The a1 they gave us, that's negative 5. And then for the r value, that's what I multiply by in the recursive part, so this 1/4. So we have negative 5 times 1/4 to the n minus 1. For this word problem, we have a music streaming service that initially has 50,000 members, and then each year the company loses 20% of its current members and gains 5,000 new members. So we want to start by writing a recursive rule for the number of members at the start of the nth year. So let's start with our base case here. So we've got, I'll call it a sub 1. That's the first year. So at the start of our first year, we have 50,000 members. And then if we're losing 20 and gaining 5,000, that means we have to take our previous value, we'll call it a sub n minus 1, and multiply it by 0.8. That's what losing 20 looks like as a percentage. So 0.8 times a sub n minus 1. And then we also have to add 5,000 for those new members. So this is our recursive rule that we can now use to figure out anything we want. What do we want to figure out? Well, they want us to tell them the number of members at the start of the 5th year. So let's plug this into the Desmos grapher. I have to use the graphing version, and we'll see what we can see. So here's my Desmos grapher. To do a recursive function in here, I have to enter the base case and the recursive part in separate lines. So let me, right here, I'll just put in f of 1, because this is how I have to specify it. F of 1 equals 50,000. And then for the recursive version of this, f of n equals 0.8. And now we'll do f of n minus 1. That gives me the a sub n minus 1 stuff here. And then we'll add 5,000, so plus 5,000. And then go down to a new entry level. And they wanted us to tell them the 5th year, number of members at the start of the 5th year. So that would be f of 5. And plugging that in, it does all the recursive fun for us. That's going to be 35,240 members for that year. And then for this next one, they want to know what happens to the membership over time. So if I plug in bigger and bigger numbers, is this thing just veering off into infinity? Is it leveling out? Let's find out. So instead of f of 5, let's do f of 10. And that's about 28,000 and change. How about f of 20? Well, that's a little bit less, 25,360, but it's still changing. How about f of 30? Changing a little bit, f of 40. Now we're down to almost 25,000 exactly. F of 50, 25,000 even pretty much. Can we get any lower? Let me do f of 100. Looks like we're kind of holding steady at 25,000. Let me just add another 0 for fun. 25,000. All right, I think we can conclude that we are leveling off at 25,000 members. For this problem, we're borrowing $2,000 to travel. The loan has a 9% annual interest rate. That's pretty high, and that's compounded monthly for 2 years. Monthly payment is $91.37. Okay, that doesn't sound too horrible. So we want to find the balance after the 5th payment. First, we're going to start, though, by writing a recursive rule for the balance after the nth payment. So to do this recursively, I am going to need an A1. We'll call that 2,000, and I'll actually call that A0 because that's what I start with, and then after every payment, this balance gets updated. So for the recursive piece, I need to multiply whatever my balance is by 1 plus the interest rate. And we got to be careful here because this 9% is an annual rate, but we need a monthly interest rate instead, so we'll take care of that in a minute. But we need 1 plus whatever the interest rate's going to be times a sub n minus 1, and then we have to subtract the monthly payment. So we're going to increase the balance with that interest rate, but then we're going to lose a little bit because of the payment. Now, to get the rate, I need to do 9%, so 0.09 divided by 12 because it's monthly. Let me go on Desmos and see what that looks like. So we've got 0.09 divided by 12, and that's about 0.0075. All right. So we've got 1.0075 times a sub n minus 1 minus 91.37. And this is our shiny recursive formula that we can now use to figure out whatever we want. So we want the 5th payment, balance after the 5th payment. All right, well, let's go ahead and plug 5 into this thing. Let me first set it up on Desmos so I can erase all this, and let me move this over so I can see a little bit better. Whoops. Let's see, let's try this. Okay, there we go. So we have f of 0 equals 2,000. That's my base case that I need for this to work. And f of n is going to be 1.0075 1.075 times f of n minus 1, that's my last term, and then I have to do minus 91.37. Once I've got this in there, I can just do f of 5 to get my fifth payment, and that leaves me with a balance of $1,612.38. Cool. All right, now for the second part of this, they want the amount of the last payment. So in order to figure that out, we're going to figure out what our balance is after the second to last payment, and then we're just going to multiply that by the interest rate to figure out our final payment, which might actually be different than this monthly payment. Usually it's a little bit different because of all the rounding that takes place along the way here. So to figure out the amount of the last payment, how many total payments would there be in this? We've got monthly payments for 2 years. 2 times 12 gives us a total of 24 payments. So I'm actually going to need to figure out my balance after payment number 23. So let me go to Desmos and do f of 23, and that leaves me with a balance of $90.68. So that's balance after the second to last payment. Now I'm going to multiply this by my interest rate here, so multiply this by 1.0075, and let's do that on the calculator. So I'll just multiply this up here by 1.0075, and that gives us roughly $91.36. And that is a little bit different than what we had here, the $91.37. Very close, just a cent off. But hey, we get to save a cent on that last payment. Awesome.